All right, welcome to Lecture 10 in this course on Algebraic Topology. I'm Norman Wildberger. So last time we talked about Euler's formula both in the context of polyhedra and then a little bit on graphs. Today we're going to carry on with more applications of this formula, mostly to graphs, planar situations. So let's talk a little bit about the planar graphs, which we talked about in the Euler's formula situation. So a graph is planar if it can be represented in the plane with no edges crossing. And important family of graphs are the complete graphs. So complete graphs. Well, there's just K1, K2, K3, K4, and K5, and so on. Well, I hope the pattern is clear. We're simply starting with n points and connecting them with all possible edges. It's a complete graph. And it's pretty obvious that these ones are planar, K1 to K3. K4 doesn't look planar the way I've drawn it there, but it is a planar graph, and you can see that easily just by taking one of these edges and moving it so that instead of going along from here to here, it goes, say, from here to here. K5 is not planar. It's an important example of a graph that's not planar. How can we see that it's not planar? Well, suppose it is. Suppose it is planar. Then its number of vertices is 5. And the number of edges is 10. Because the number of vertices and edges is not going to change. And since V minus E plus F equals 2, which is a formula valid for planar graphs, it would mean that F would have to be 7. So there would have to be 7 regions in which this graph cut the plane. That's including the boundary, or including the outside. Now each edge borders 2 faces. And every face has at least 3 edges. So if we count, 2 times the number of edges must be bigger than or equal to 3 times the number of faces. But the edges are 10, and the faces, well, according to Euler's formula, would be 7. So 3 times 7 would be 21, and that's not possible. There's another important graph that's not planar, and that's obtained by looking at the bipartite complete graphs. So a graph is called bipartite. if we can group its vertices into two disjoint sets, so all the vertices of one kind on this side and all the vertices of another kind on this side, so that all the edges are between vertices in this set and in this set. So something like this. That would be an example of a bipartite graph. Okay. So then there's the complete bipartite graphs. Well, if there's just 1 and 1, so we might write K11, that's just going to be like that. And then if we have 2 here and 2 here, K22, well, that would be all the possible edges that we could draw, keeping this set and this set as the two basic sets. And K33, 1, 2, 3 on this side, 1, 2, 3 on this side, K33, so all possible edges. And it's a sort of a well-known party trick or something that the source of many popular puzzles, that K33 is not planar. If you have 3 houses and 3 utilities, you can't connect the houses to the utilities in a planar way. All right. So problem 13. Show that K33 is not planar. The importance of these two particular examples are due to a famous theorem called Kuratowski's theorem. Which is that a graph is planar, the graph X is planar precisely when it does not have K5 or K33 as a subgraph. So if you have some very complicated graph and you're trying to figure out whether it's planar, it might be simpler to look around to see if you can't find any complete 5 graphs inside or any complete 3 bipartite graphs, and then you could reason that it's planar or not planar.
What do you mean by subgraph?
Okay, that takes a little bit of explaining. Maybe I won't explain it. Okay, yeah. It's not going to be important for us. I just want to mention it why the two graphs are important. Okay, so what I do want to talk a little bit about is a theorem called the 5 neighbours theorem. And this is closely connected to this famous 4-coloring problem that, well, you've probably heard about, that an arbitrary planar graph can be colored with a planar map can be colored with 4 colors in such a way that no 2 neighboring countries have the same color, the 4-color problem. And this allows us a very quick but weaker version of that very big theorem. And so the 5 neighbours theorem says that every simple planar graph has a vertex of degree 5 or less. And I remind you that the degree of a vertex is just the number of edges coming into it. Every simple planar graph has a vertex of degree 5 or less. Okay, so proof. We're going to enlarge the graph by adding edges. So all faces are triangles. And still planar. So I suppose if we had something like that.
So presumably we're not counting the outside face there.
Oh, it's a simple graph. So this is a parallel. These are parallel edges there. Maybe I'll make a. No, the outside edge is also, the outside face is also included in this. Okay, how do we make this into triangles? Okay, well, you just look for a face which is something else, like that one there, and you just, okay, there, now that face is now a triangle, or two triangles. Here's another 4 face, so we'll make it to a bunch of triangles. What about the outside? Oh, it's got lots of, how do we make that into triangles? I suppose if we do that, then that's another triangle. And then that's another triangle. And I'm making, that's another new triangle. That's a new triangle. That's a new triangle. That's a new triangle. How many sides does the outside have now? 1, 2, 3, 4. We're almost there. So suppose I join this one with this one. Now I've gotten, that's a new triangle, but now the outside only has 3 edges around it, so it's also a triangle. Okay, I'm going to prove that that thing has a vertex of degree 5 or less. So since I've only added edges, if that has a degree of a vertex of degree 5 or less, then the original will also have a vertex of degree 5 or less, because I've only added edges. All right, so now we suppose, now we have V, E, and F, vertices, edges, and faces. And we know that since each of the faces are triangles, that 3 times the number of faces is 2 times the number of edges. Counting edges. Each face gives 3 edges. So if you count them all that way, you get 2 times the number of edges. And of course we know Euler's formula, V minus E plus F equals 2, which we'll rewrite for convenience as 6E minus 6F equals 6V minus 12. I'm just multiplying by 6 and rearranging. And now I'm going to replace over here, this is the same as saying that 6F is the same as 4e. So I'm going to replace the 6f with 4e. So I get 2e equals 6v minus 12. Okay, I replace the 6f here with the 6f there, with the 4e. 2e equals 6v minus 12. Okay, the sum of all the degrees is, like, look at the degrees of all the vertices. It's the number of edges coming into each vertex. I'm just going to get twice the number of edges, counting each of the edges twice. So the sum of all the degrees is 2e. So the average degree is going to be the total degree, the sum of all degrees, divided by the number of vertices. I have v vertices. The sum of all these degrees is spread out amongst them rather irregularly, but the average is 2e over v. And according to this formula, that's this divided by v. That's 6v minus 12 over v. That's equal to 6 minus 12 over v. In particular, that's less than 6. So the average degree of this big extended graph that I've made, the average degree is some number less than 6. But there must be then at least one vertex which has degree 5 or less. They can't all have degree 6 or more, because then the average couldn't be less than 6. So at least one vertex is of degree 5 or less. And that's the end of the proof. All right, so as a consequence of that, we'll prove a theorem that the 6-color theorem that every map, every planar map, can be colored with 6 or fewer colors. Okay, we actually know, it's a highly non-trivial theorem of Appel and Haken. It's a very well-known and somewhat controversial theorem because it relies on a huge amount of computer calculation. So Appel and Haken in 1976 shows that 4 colors suffice. That's the result of a huge amount of work and a great amount of computer calculation too. 5 colors is not so bad, but we're going to prove 6 colors very cheaply here. All right. So in graph theoretic terms, instead of thinking about a map with countries, we just rather think about the corresponding adjacency graph. So we'll just put a vertex for each country and connect the 2 countries if they're adjacent. Then we can forget about the map and just concentrate on the graph, which is somewhat simpler. And then what it amounts to is saying that we can color the vertices of the graph with 6 colors so that any edge always separates the 2 vertices on the end of every edge are a different color. So the graph version, if we have a planar graph can be vertex colored with six colors. So no two adjacent vertices ones have the same color. That's what we want to prove. Given a planar graph, 6 colors, we can color the vertices: red, blue, green, purple, white. Red, blue, green, purple. So that when you look at any edge, the 2 colors on that edge are different. And we'll use this 5 neighbours theorem. Proof. If not, find a counterexample with 6 or fewer colors. Well, find a counterexample with the smallest number n of countries. So suppose you come to me with a graph and you say, here's a graph that I know you cannot color with 6 colors. And it's the smallest one. There must be a smallest one. One of the smallest number of such vertices. I mean, maybe you can get a counterexample with 27. Somebody else can get up with a counterexample with 21. Okay, whatever that number is, I have here's this minimal counterexample. So what do is, well, we remove a vertex of degree 5 or less. We know that exists from the previous theorem. Now that's a smaller graph, so it can be colored. So this can be colored. With 6 colors. So we color it with 6 colors. And now we put the removed vertex back. And color it with what? Well, it's only connecting to 5, at most 5 of the other countries. So it's only connected with 5 other colors at most. And so that extra vertex, we can use the other color which is not being used to color it. And then it will be different from all its neighbors. And then we'll have colored the graph that you claimed was your minimal graph that couldn't be colored. But as I say, now put the removed vertex back. Okay, put the removed vertex back and color it with the other color from its neighbors, from its 5 or fewer neighbors. That's a contradiction, and so our assumption is incorrect. All right, so for my last application, I'm going to prove an important and also famous result called Pyxis Theorem, which is a surprisingly useful little theorem. So Pyxis Theorem, which tells us how to compute the area of a polygonal region in the plane whose vertices lie on the unit lattice or on the standard lattice. Okay. So it's a theorem about areas. Area of a polygon in the plane with integer vertices. So, for example, I have to create a little grid here. So let's create 1, 2. Okay, there's it's like it's the standard lattice in the plane. You can imagine they're each 1 unit apart. And let's say we have a polygonal region whose corners are on our grid. Say that one right there. Suppose we want to know what the area of that thing is. Well, of course, in this case, you wouldn't be too hard. You could cut it up into little squares and triangles. But you could imagine a much more complicated thing. It might be painful to have to cut it up into lots of little triangles and add them all up. So Pyxis theorem gives us a formula for the area in terms of the number of vertices that lie on the boundary and the number of interior vertices. And the formula is that the area, A is the area, is I plus B over 2 minus 1, where I is the number of interior points and B equals the number of boundary points.
Do you include vertices?
Sorry?
Do you include the vertices?
Yes. So in this case here, what should A be? In our example, the area should be I. The number of interior points is 4. 1, 2, 3, 4 points there. That's I. Number of boundary points. 1, 2, 3, 4, 5, 6, 7. So 7 over 2. And then we have to subtract 1, which is 6.5. Let me just check that that's correct by doing a little bit of calculation here. So in this case, it's not too hard. This area here is 2 by 2, so that's area 4. I suppose if I make a little thing like this, and that's 2 by 1, so that's going to have area 2 times 1 over 2. That's area 1. And here the area is 1 times 1, 2, 3. So that's 1 times 3 over 2. 3 over 2. 4 plus 1 plus 1.5. It's also 6.5. And this is called Pyxis Theorem. There it is right there. Okay, let me just remind you, if you're in the plane and you have a vector AB, let's say, and another vector CD, then the area of this parallelogram, the area of the parallelogram is the determinant of A, B, C, D. So that's AD minus BC. Right? And so the area of the triangle, the area of this triangle would then be half of that. So this area would be, area of the triangle would be AD minus BC over 2. This being a determinant, it's actually a signed quantity. It could actually be negative if the orientation of the two vectors is the other way around. But so in particular, if you have a triangle made out of integer points with integer coordinates, this number is always either an integer or a half integer. So it's always an integer or half integer. In particular, the minimum that it can be is a half. The minimum possible area, minimum possible area for the triangle is a half. Or for a parallelogram, it's 1. Now, that's for integer triangle. In other words, I'm talking about the case when all these numbers A, B, C, and D are all integers. Now, a primitive triangle is one with, or primitive integral triangle. Okay, I'm only talking about integral triangles. That is ones where the corners or the vertices are all have integer coefficients. Yeah, that's all I'm going to be talking about. But a primitive such triangle is one with no interior points and only 3 points on the boundary. And Pyxis Theorem, there's a special case then, the special case when we just have a triangle for which there's 0 interior points, 3 points on the boundary. Pyxis Theorem is telling us that such a primitive triangle has area a half. So this is actually a lemma. This is a special case of Pyxis Theorem. The lemma is that a primitive triangle primitive integral triangle has area 1/2. We need this lemma to prove Pyxis Theorem. It's a special case, but we sort of use that as a building block. So we need to give a separate proof from Pyxis Theorem. Can't use Pyxis Theorem to prove this because we're going to use this to prove Pyxis Theorem. So the argument is a little bit complicated, but the idea of it is pretty simple. By the way, how do you get such a primitive triangle? You get it by picking a matrix whose determinant is 1. The minimal possible for an integer matrix. For example, you could choose a 4 times 7 and 3 times 9. So that means if I take the vector 4, 3, something like this, 9, 7, the point is they're roughly in the same direction. They might be rather long vectors, but they're long and skinny. And this triangle, or it's probably maybe a little bit easier to think of the associated parallelogram. So the associated parallelogram, it's not so easy to draw, but it's very long and skinny. But it only has 4 integer points on it. Think about that parallelogram. Okay? What I want to do is I want to convince you that that parallelogram has area 1. Then the triangle will have area 1/2. So what we know is that this is a parallelogram with only 4 integer points on it. And I want to convince you that its area is actually 1. So this parallelogram has 4 integer points, and that's all. And I want to convince you that its area equals 1. Okay, so what we do is think about the lattice of all integer points. Okay, so imagine this lattice. And imagine taking this parallelogram and taking all of its translates to tessellate the plane. Now, any parallelogram will tessellate the plane, right? If you have a parallelogram like this, you can shift it over by 1, and it will tessellate, fill up the plane. So what I want you to imagine is taking this lattice, but at a very big scale, maybe 1,000 this way by 1,000 this way. And I want you to imagine tessellating that whole region with copies of this parallelogram. Okay. Now, each of these parallelograms occupies 4 points. And each one of these squares also occupies 4 points. So if you consider this huge region of 1,000 by 1,000, or maybe 1,000,000 by 1,000,000, I claim that the number of parallelograms and the number of squares is pretty well the same. Because I've got to cover all of the points in there, 1,000 squared or 1,000,000 squared. And each square takes 4 points, and each parallelogram takes 4 points. So they're each taking 4 points at a time, so the numbers of them have to be roughly the same. Not exactly, because this one's long and skinny will stick out a little bit beyond the boundary. It won't be exactly the same, but if I take a big square, then they'll be practically the same. Do you buy that? So I'm just taking in terms of the numbers of points. Just to cover all these lattice points, a square covers it 4 at a time. So does the parallelogram. Therefore, there must be roughly the same number of parallelograms as squares. And now, since there's the same number of parallelograms in this big block as there are squares, the area of the parallelogram has to be the same as the area of the square, namely 1, because they're both covering this very big blob. That's an idea. Okay, you have to make that a little bit precise if you want to do it completely correctly, but you can kind of intuitively see that that's reasonable, I hope. Okay, so I'll leave. I won't write that down. There's the argument, and so we'll assume that we've proven this lemma. The main point is I want to show you how Euler's formula allows us now to get at Pyxis theorem, assuming this lemma. Okay, so suppose we have our polygon now. Now this is our proof of Pyxis theorem. Proof of Pyxis formula. So I'll write that again. A equals I plus B over 2 minus 1 for the area of our polygon T. Let's call the polygon. No, there's our polygon. And it should be convex, yes. Maybe I didn't say that. It's a convex polygon. Thank you. So these are all integer points. And there are some integer points inside and on the boundary. I haven't shown them. Okay, so the first thing we do is we subdivide into primitive triangles. Let's say T of them. So whenever if we go along here, we find a point on the boundary. We can go along here, we find a point on the boundary, we can just, there's a primitive triangle. If there's something else inside there, well, then we have to keep subdividing. Keep subdividing whatever we've got using the integer points only until we can't subdivide anything further. So we have T primitive triangles. So the number of faces, well, we've got this now, this pattern of very skinny triangles, all primitive. Okay, it's hard to draw them. Let me draw them pretend it's something like this. Okay. They're actually all skinny and long, generally. So we've got T primitive triangles, and we look at this as like a graph, like we have been before, and we've got the number of faces is going to be T plus 1 because we have to include the boundary, the outside, for Euler's formula to work. And the area is, by our lemma, just T over 2. That's the quantity A that we're interested in. Because we're assuming the lemma that we've proven that a primitive integral triangle has area half. So if there are T of them, then we have T over 2 as the total area. Okay, so 3 times T counts each edge twice. Except for the boundary edges. Which are counted once. Now the number of edges on the boundary, if you just walk along the boundary and count edges, so there's one edge, there's another edge. The number of edges on the boundary is the same as the number of vertices on the boundary. Because it alternates vertex, edge, vertex, edge, vertex, edge. And so that's what we are calling B in our formula. The number of vertices on the boundary is B. So the number of edges on the boundary equals the number of vertices on the boundary that's equal to B. Okay, so when we go back up to here, this 3T that we were counting, it counts each edge twice, except for the boundary edges, which are only counted once. So we have to remove from this the boundary edges that we've counted twice. And there's exactly B of them. So we have to adjust this total by subtracting B, the number of boundary edges. The total number of vertices, well, it's the number of vertices on the boundary plus the number of vertices in the interior. So that's I plus B. Okay, so let's have a look at what Euler's formula says. Euler's formula for this planar graph, 2 equals V minus E plus F. Okay, so what are these various things? V is equal to I plus B. From over there. Minus the number of edges. Well, the number of edges we can solve from here. 3T plus B over 2. 3T plus B over 2. I'm going to separate it like that. Plus the number of faces, which we have from here, plus T plus 1. And what does that all amount to? So T. Okay, there's an I plus B over 2. B minus B over 2. And there's a T minus 3T over 2. That's minus T over 2 plus 1. And so, well, the 2 and the 1 will simplify. We can bring the T to the other side. So we have T equals 2 times I plus B minus 2. And A, which is what we're really interested in, and A, which is T over 2, that's equal to, just divide this by 2, I plus B over 2 minus 1. There's our formula. Pyxis Theorem.
So, how do we know we can subdivide into primitive triangles?
So you just concentrate on where all the integer points are. So let's say you've got one triangle which is not primitive. What does it mean? It means that it might have a point in the interior. If it does, you just connect it like that. And now you have small things. Or it might have a point on the boundary. If it does, say that one there, you can just go like that. So that way we just keep going to make sure that we can subdivide any triangle into primitive triangles. Okay, so next time we are going to talk about another aspect of Euler's formula that actually goes back to Descartes. Descartes almost had Euler's formula. He was thinking in terms of curvature of polyhedra, and we're going to talk about curvature. And that's going to be something that probably will shed light even on the planar situation, things that are rather familiar to you. We're going to have a look at even triangles and polygons in the plane in a new light. That's what we're going to do next, and I'll see you then.